Hello, my name is Rob Agox, and I'm part of the TRAK capstone design group that built the Sunbox solar panel deployment system for automotive applications. Here's an outline of what I'll be talking about. I'll go over our problem statement, our design tools, design analysis, design models, our prototype, our production analysis, and finally our conclusion. We were tasked with the challenge of designing a deployable solar panel system for the Ford C-Max solar energy vehicle. The deployed area must exceed 5 square meters in order to fully charge a car battery in 8 hours. The design is to be fully self-contained with no off-board infrastructure, allowing for a maximum freedom in charging the vehicle. The device also needs to be lightweight enough to save on fuel economy so the vehicle is not significantly compromised at stable and high speeds. The Ford C-Max solar energy concept was released in 2014. It was intended to harness the power of the sun by concentrating the sun's rays to generate enough power to fully charge the battery within 1 day. Unfortunately, the lens posed problems with the panel's overheating. Our challenge is to generate the same amount of energy without the Fresnel lens by increasing the surface area of the photovoltaic panels. Standard solar panels are mounted on an aluminum frame to provide a lightweight and corrosion-resistant support system. The solar glass is typically tempered glass to provide much higher strength than untempered glass. It also has the benefit, especially in this application, of shattering into a bunch of very small pieces rather than long, sharp shards. The cells are adhered and protected against UV aging and weathering with an encapsulant film. The photovoltaic backsheet is designed to protect the inner components of the module, specifically the photovoltaic cells and electrical components from extreme stresses, as well as act as an electric insulator. Lastly, there's a junction box mounted to each panel to prevent reverse current flow. Currently, there are no vehicles on the market that utilize onboard solar energy systems to fully charge the battery. However, the Toyota Prius, Fisker Karma, and Audi A8 have solar panel add-on options that utilize solar panels to power small electronics within the vehicle, such as fans and the stereo system. Relevant concept designs such as deployable solar panel systems or fully solar-powered vehicles were also explored. These are just some examples of fully solar-powered car concepts. None of these are actually on the market for consumers, but these were explored by our group as just springboard points. The Volvo Solar Pavilion is a concept design that can charge a Volvo's car battery in 12 hours. The structure collapses such that it can fit inside the trunk. The downside to this design is that it is so large when deployed that it would not be usable in a standard parking lot. The solar shelf shade is a manual fold-out system that stores inside the spoiler of the car. Because these panels are relatively inefficient, this design only provides enough power to operate some interior electronics and the air conditioner. Considering the specifications and the competition, a list of what to keep in mind for the design phase was put together. First, safety is key, since every unsafe feature is magnified many times when driving at 60 miles an hour. Affordability is also important since the product is being marketed to consumers. The design must also be aesthetically pleasing because it will be on vehicles which owners will take pride in. Quick deployment is also important so purchasers find it worth their time to actually use it. It must be lightweight to avoid serious reduction in gas mileage. A low-maintenance design is also important so that the average person can keep it working without a specialist's help. Lastly, a universal attachment system would open up the market, allowing the design to be usable on all hybrid and electric vehicles. Here's a Gantt chart used by our team to keep track of important deadlines and to figure out what must be done to prepare for each deadline. This is the beginning of our market research. It was decided that our high-influence, high-impact market would be the Ford Motor Company, which creates the Ford C-Max solar energy hybrid car, and also all consumers of automobiles. Those who we shouldn't pay much attention to would be people who could not afford to drive in the first place. Our target market, therefore, consisted of mobile users with considerable disposable income who are idealistic in that they think they can change the world with just a solar car. This led us to target a market including young business professionals, older people with progressive outlooks, and those with media influence. This is the result of our market survey, which gave us the customer expectations and needs. Those bars that you see that are above the center line are the specifications that we should pay highest attention to. An evaluation matrix was created to develop a relationship between the needs of the customer and the technical design requirements. The absolute ratings help prioritize the technical requirements of the design. A low-profile design and lightweight materials were found to be the most important design parameters to account for. Based on the aforementioned information, some specifications were set to outline the functions to be met with the design. Most importantly, and based on market research previously done at Georgia Tech, the surface area required by the photovoltaic cells was 5 square meters. This will be able to fully charge a Ford C-Max Solar Energies battery in 8 hours. The maximum fully deployed dimensions were determined to be 8 feet by 16 feet, which is the size of a compact car parking space. The system must also be self-contained for convenience. The deployment time must be less than 60 seconds for additional customer convenience. Additionally, the storage size of the system must fit non-intrusively on the vehicle to avoid hurting the aesthetics. The maximum weight of the system should be less than 300 pounds to avoid decreasing the vehicle's mileage by a significant amount. The function tree is a tool that engineers use to break down several vague functions of the desired system into several smaller subsystems. Each can be accomplished in a small amount of time. In this function tree, the main goal is to create a mechanism that deploys solar panels over 5 square meters, and then retract the panels. The large system is broken down into several smaller subsystems, each of which plays a role in accomplishing the final goal. A morphological chart was used as a brainstorming tool to generate different solutions that could be used to meet specific functional requirements of the design. The main functions of the device were broken into 3 categories: activation, storage, and deployment. From this chart, we were able to refine our design to include fully manual activation that deploys laterally from the roof of the vehicle and is stored on top of the vehicle. During the concept ideation phase, the team drew up and described any ideas that came to mind to accomplish goals, with these being some of the resulting drawings. A failure modes effects analysis was completed to identify and quantify the risks associated with the design. As seen in the figure, the highest risk is associated with the panels not deploying at all. It should also be noted that this is a failure mode specific to the prototype itself because the gears were small due to cost constraints. Partial deployment and cracking were also high priority risks. Partial deployment is a failure mode associated with the prototype itself, and the cracking of the panels would be a problem in the manufactured device. To combat cracking of the panels, airtight storage would be integrated into the design along with a damping material to lessen vibration. For the prototype, a different set of materials were used in order to fit into the time, cost, and manufacturing constraints faced by our project team. The system was much sturdier, heavier, and bulkier than necessary, but these issues could be fixed using angled aluminum instead of aluminum tubing in order to reduce the weight, and a custom plastic mold to provide a more aesthetically pleasing and aerodynamic design. Before beginning the build process, a set of technical drawings were made to assist with the machining process. Each of these drawings provide all the required dimensions for cutting all of the tubing to appropriate lengths and drilling out holes for fastening used to connect all the pieces and mount to other parts, such as the drawer sliders used for extending the solar panels out from the frame. 8 different drawings were made to account for the various tubing sections. This is the final SolidWorks assembly model, pictured with the solar panels on the left and without the solar panels on the right. On the left is an exploded view of one of the side panels and the parts used to mount it and extend it out over the main frame. On the right is an exploded view of the gear system used, including 4 rack and pinion subsystems and a sprocket and chain subsystem to ensure the front panel extends in unison with each of the other side panels. The front, back, and side panels each extend 42 inches, 27 inches, and 18 inches respectively. The gear ratios to accommodate these lengths were calculated. With these known, a set of gears were chosen at the ratios necessary in order to allow for each of the panels to be fully deployed at the same time simply by pulling out the front panel. The stress analysis shows that the system is over-designed because the maximum stress in the structure is 4 ksi and the yield strength is around 40 ksi, and most of the structure shows about 0 stress. For this prototype, material selection was somewhat limited due to cost constraints as well as the standard parts available for the application. The drawer slides used in the design govern the size of the aluminum square tubing that was used in the prototype. The 60-inch drawer sliders were 3 inches wide, so that 3-inch aluminum square tubing had to be used for support. Utilizing more angled aluminum as opposed to tubing might be an effective way to combat this issue in the future. The deflection analysis shows a maximum deflection of 0.85 inches in the aluminum supports. In order to combat this relatively large deflection, diagonal cross supports were added to the extended lateral support structures. The panels mounted on the supports will also have a frame around them which will reduce the amount of displacement in the cross supports, most likely banishing the need for the cross supports altogether, which will therefore lower the weight. Suspension vibration was measured at 7.85 radians per second. This would be critical in protecting against fatigue. The vibration equations were solved for a 4-spring single degree of freedom suspension system. It's noted that the specific expanded expression only holds true for an input amplitude of 1 meter. However, the total displacement will scale linearly with any input amplitude. These are graphs of the ratio of output amplitude to forced amplitude and the phase angle shift as functions of spring constant and damping coefficient. Note the resonance experienced at 875 newtons per meter. It can be seen that a band reject filter behavior centered at the necessary forcing frequency is displayed when the spring constant is set to 5.43 pounds force per inch, and the damping coefficient is set to 6.85 seconds pounds force per inch. These are some photos of our entire build process. A bill of materials for the prototype was developed. It's noted that the most expensive materials bought were the 3-inch aluminum tube and also the 3-inch drawer sliders. Our total cost was $881.44. We were budgeted $800 for this project. A design validation figure was created to help quantify the characteristics and ensure that all of the specifications were met. In an attempt to decrease the charging time, the total surface area was increased, resulting in an extra 0.2 square meters of surface area. For deployment time, the specifications were easily met because of the manual one-action deployment. The fully extended lateral dimensions also easily met the specifications. Our design is both effective and unique. It provides enough power to fully charge an 8 kilowatt-hour battery in 8 hours, and is a universal design that can be implemented on any hybrid vehicle. It is also non-invasive and detachable, allowing for maximum flexibility for the user if the system needs to be removed. Lastly, it is an entirely self-contained device requiring no off-board infrastructure. The driver can use the system at any time, anywhere, without the need for an off-board power source. For a future version of the design, the next generation materials mentioned before would be used, reducing the overall weight and improving aesthetics of the system. A spring system would also be added in accordance with the vibration analysis, improving survivability of the solar panels when in transit. Additionally, a custom roof rack system would be required in order to support the increased total weight of the system due to the addition of real solar panels. Lastly, here's a video of our prototype in action.